Good morning, students. This is the second lecture on the chapter Gas Turbine and Jet Propulsion. Myself Devojit Devanji, lecturer in Mechanical Engineering at Raiganj Polytechnic. In the previous lecture, we learned about the different aspects of the Brayton cycle, and in this lecture, we will study about the methods to improve the thermal efficiency of gas turbine, namely regeneration, intercooling, and reheating, and their TS diagram. So, there are mainly three methods for improving the thermal efficiency of gas turbine. They are regeneration, intercooling, and reheating. So, let us first talk about the effect of regeneration on Brayton cycle. Now, what is the regeneration? What is the basic idea? The efficiency of the Brayton cycle can be increased by utilizing part of the energy of the exhaust gas from the turbine in heating up the air leaving the compressor in a heat exchanger called as regenerator. Right? If you look at the figure, thereby reducing the amount of heat supplied from an external source and also the amount of heat rejected. Such a cycle is illustrated in the figure. The temperature of air leaving the turbine at 5 is higher than that of air leaving the compressor at 2. In the regenerator, the temperature of air leaving the compressor is raised by heat transfer from the turbine exhaust. The maximum temperature to which the cold air at 2 can be heated is that of T5, that is the turbine exhaust. But practically it is possible only in an infinite heat exchanger. So in real case, the temperature T3 is less than that of T5. Okay, the ratio of the actual temperature rise of air to the maximum possible rise in air is called the effectiveness of the regenerator. In this case, the exhaust effectiveness will be equal to, that is the practical increase, that is T3 minus T2 divided by the theoretical increase, that is T5 minus T2. When regenerator is used in the idealized cycle, the heat supplied and the heat rejected are each reduced by the same amount. The mean temperature of heat addition increases and the mean temperature of heat rejection decreases because of the use of regenerator. Thus, the efficiency is increased as a result, but the work output of the cycle remains unchanged. Okay. So, because of this, because of the mean temperature of heat addition is increased and that of heat rejection decreases, the efficiency increases. So these are the basic equations of the regeneration. Now some issues. Now in practice, regenerator is costly, heavy, bulky and causes pressure loss, which brings about a decrease in cycle efficiency. These factors have to be balanced against the gain in efficiency to decide whether it is worthwhile to use the regenerator or not. Right? There are above a certain pressure ratio, the addition of a regenerator causes a loss in cycle efficiency when compared to the original Brayton cycle. In this situation, the turbine discharge temperature is higher than that of turbine exhaust temperature. So, compressed air will thus be cooled in the regenerator and the exhaust gas will be heated. So, our purpose will not be filled. Thus, as a result, both the heat supply and heat rejected are increased. However, the compressor and turbine works remains unchanged. So, the cycle efficiency decreases. And also, there are irreversibilities involved in the turbine and compressors. And the Brayton cycle is highly sensitive to real machine efficiencies of turbine and the compressor. For example, 3 to 4 this is the isentropic process, but because of irreversibility, the actual process is 3 to 4. So clearly, the work obtained from 3 to 4 in the turbine is clearly less than the work obtained from 3 to 4s. And similar pattern, work consumed in ideal case by the compressor is H2s minus H1, and in real case it is H2 minus H1, which is more than H2s minus H1, as can be seen from the figure. Now let us discuss the effect of intercooling on the Breton efficiency. The efficiency of the Breton cycle may often be increased by the use of staged compression with intercooling. Let the compression process be divided in two stages. Right? Air, after being compressed in the first stage, is cooled to initial temperature. That is, by means of this intercooler, after initial compression, this T2 is brought to T1 and then sent back to the second compression, right? It will be more clear if you look at the TS diagram and PV diagram of the figure. So 1 to 2 dash to 56, that is 1 to 2 dash to 56, this was a basic cycle. Now this is without intercooling, having a single stage compression, and 1 2 3 4 5 6 1, this is the cycle with intercooling having two stage compression. Thus the cycle, that is 2 3 4 2 dash, this portion is added to the basic cycle. Thus area increased or work obtained will be more. Now there is more heat supply also. For this cycle, for the cycle 2342 dash, Tm1, that is the mean temperature, Tm1 is lower and Tm2 is higher than that of the basic cycle 12-56. So the efficiency of the cycle reduces by staging the compression and intercooling. But if a regenerator is used, that is the low temperature heat addition 4 to 2 dash may be obtained by recovering the energy from the exhaust gas from the turbine. So there may be a net gain in efficiency when intercooling is adopted in conjunction with a regenerator. This is the TS diagram and this is the PV diagram. 1 to 2 is in compression, first stage compression, 2 to 3 is the intercooling process, 3 to 4 is the second compressor, is the process in second compressor, 4 to 5 is the combustion chamber where Q1 heat is added at constant pressure, 5 to 6 is the turbine isentropic expansion, and 6 to 1, that is heat rejection. Okay. So it is shown. Now, as we discussed, the intercooling may improve the efficiency of the compression, but overall thermal efficiency of the cycle will decrease. The way to increase the intercooling efficiency is to use intercooling accompanied with regeneration. Right? In the next lecture, we will start about reheating, the effect of reheating on the Breton cycle efficiency. So for the time being, we stop here and we will discuss on this topic in the next lecture.